Hello, my name is Jemima Junkier and I am working with Sean Alman on this Yugo project. I am a mechanical engineering major with a minor in mathematics, while Sean is a mechanical engineering and computer science major. We are both students of Midwestern State University in Wichita Falls, Texas. Under the mentorship of Dr. Salim Azuz, we have been investigating desalination using an electric field across a seawater channel.
The motivation for this project is that freshwater shortages can destabilize society, cause political unrest, and trigger mass migration. This map shows the depletion of water across the world. The red areas use more water per year than they receive. Eventually, the red areas are going to run out of fresh water, and so desalination is a must.
This slide gives a visual representation of the distribution of the Earth's water. As you can see, 98% of water is found in seas and oceans, that is salt water. 1% is trapped in ice and inaccessible. Only 1% is actual fresh water, with a 0.5% being found on the surface and another 0.5% being found in the ground.
The goal of this project is to design a low energy consuming, mechanically driven machine to separate the sodium and chloride ions from a brine solution using an electric field across a flowing seawater channel. These are the images of the model and the idea that we proposed. The image on the left is the base model that we started with. After researching, we altered the model and made it 3 channels. The seawater will flow from the top left to the bottom right. Four turbines will be rotating from the middle channel to the outer channel. These turbines will be electrified while in the middle channel. One set of turbines will be electrified positively while the other one will be electrified negatively. This will ensure that the turbines grab a hold of the sodium and chlorine ions. Then the turbines will rotate to the outer channels where they'll be de-electrified, dropping the ions into the outer channels. Therefore, the middle channel output will be desalinated, while the outer channels will be saturated with ions and will have to be disposed of. Because the water will never actually come in contact with the charged turbines, because they'll be coated with material, there will be very little energy consumption. The rotation of the turbines will be the cause of most of the energy consumption.
In this project, we investigated a low-cost method of seawater desalination where the positive sodium ions and negative chloride ions in salt water are affected by an external electric field. Let us first discuss the general theory of ion movement in the presence of an electric field. We considered an ion of concentration C dissolved in a water solution flowing in the streamwise direction of a duct of width L, as expressed in Figure 2. This concentration is of steady state. In an article written by Batsis et al., we observed a differential equation established by chemists governing the local concentration as a function of the electric field. The equation as expressed here as equation 1 uses Avogadro's constant and mu as the electrochemical potential. This equation represents an equilibrium state where the velocity and acceleration along the y-axis is equal to 0. By substitution and taking into consideration the gas constant R and temperature T, equation 2 was observed. By substituting for E and alpha subscript EQ, which is the activity, or in other words, the effective concentration in which an ideal solution has the same properties of a given real non-ideal solution, we were able to observe equations 4 and 5. By solving the differential equation and considering y equals 0 at one side of the duct and y equals L at the other side, and also considering an initial concentration, C0, we observed equation 6, where C subscript EQ is the current concentration when an electric field is established through a solution in equilibrium, and L is the length of the channel. C EQ over C0 represents the relative concentration in the solution. In equation 6, A is equals to Z by F by E all over R by T, where Z is the number of overflow protons and electrons. F is a constant, 96,485.34 coulombs per mole. R is a gas constant of 8.314 joules per mole by Kelvin. E represents the electric field in volts per meter, and T is temperature, represented in Kelvin assuming to be 300 K. Draw your attention to Figure 1, which represents our desalination apparatus. The four grids will be used to create the electric field. The length of the duct is represented in the channel of the length of the two channels. We spent quite a bit of time analyzing this theory so that it can be applied to our machine. From equation 6, we were able to reproduce, using MATLAB, graphs observed by Batsis and his colleagues. The graph shown represents the ion concentration along Y over L for various electric fields. In the first graph, L is equals to 0.001 meters. For an electric field of 1 volt per meter, there is almost no change in the positive sodium concentration. It is at 1, which means it is evenly distributed throughout the entire channel. This is represented by the blue line. As the electric field increases, observe that the concentration drops on the left positive electrode and increases on the right negative electrode. For an electric field of 100 volts per meter, there are almost no ions found on the left electrode, with a higher concentration on the right, as represented by the green line. In graph 2, we observe a longer length of 10 centimeters. As the electric field increases, the positive sodium ions are concentrated near the right electrode. We've noticed that with the increase in length, there are almost no ions near the positive left electrode. We observe that there is a particular threshold of electric field where the ions start to move. This seems to be about 30 to 40 volts per meters.
Now I'm going to talk about the concentration distribution as a function of channel width. So if we look at the left image, the left graph, this is for a weak electric field. So for a weak electric field of 1 volts over meter, as the width increases, we see that there's a drop of concentration of the Na plus ions on the left electrode and an increase of concentration on the right electrode. Thus, the width of the duct affects the rate of ion concentration. And we can see that the biggest width, it does pull so a 1 over here means that you're very close to the edge, very close to the electrodes. And we can see the closer we get to the electrodes, the more of a pull there is. But because of the weak electric field, we see that it only goes up to like the number, for example, almost 8 when the width is at a 0.2. But now on the right graph image, we see that this is a higher electric field of 100 volts per meter. Now the majority of the Na plus ions are concentrated on the negative right electrode as the width of the channel increases. So we see for a very small width, we do get some pool of electrons as we approach the electrode. As we go from left to right, we're approaching that side electrode. And but we can see that since the energy is so high, when the width of the duct is a little bit bigger than the smallest, we can see that it's just pulling the ions all the way towards the electrodes. In conclusion, we highlighted the importance and necessity of desalination. We studied the equation proposed by Barthes et al., and we were able to reproduce the theoretical results that he obtained on the impact of an electric field on the motions of ions across the channel. And we also improved the current design by adding a third channel with turbines that mechanically move the ions. We'd like to give special thanks and acknowledge our mentor, Dr. Azus, and Dr. Rincon Zachary, as well as Ms. Julie Scales. We also have reference to this paper, which we referred to multiple times throughout this presentation. We want to thank you for your time and attention, and if you have any questions, please let us know.